Okay, hello everyone. We're going to be talking about recursion some more today and the master theorem. And there's going to be a little bit of repetitive slides at the very beginning, partly because if we were doing this in a normal semester, we might have just gone from a Thursday to a Tuesday. So we did this problem yesterday where we were doing the log n multiplications to produce x to the n power. The 281 stickers, yes. When things are back to normal, we will put a big bunch of them outside our offices and leave them there for people to pick up. So we use the two different definitions for the formula for how to calculate x to the n power. So one way was with the just x times x to the n minus 1. The other is taking advantage of powers of 2. Now, with the second recurrence relation here, we've actually split it up into the even equation and the odd equation. Now, when we looked at the time for this, we only really considered both of these to be one group. And the reason we did that was because we didn't want to make the formula too complicated. Also, these two formulas really only differ by a constant amount of work anyway. So when we do the recurrence relationship for the time, we don't want to make it too hard. Okay, so we've got our code. We already went through the code yesterday. And we got our recurrence relationships. We went through and solved it. And went through all of this before, solving this recurrence relationship. We did this yesterday. And like I said here, we've only got in the timing, we've only got one equation when n is greater than 0. Like I said, they differ there. We could just say, hey, C1 is the largest constant amount of work of the two sets here. So that C1 represents the biggest constant amount of work in these, which includes the extra multiplication for the larger one. So we already solved this. We got big theta of log n in the worst case. In the best case, we could always get lucky and find it at the middle. But in the worst case, it'll take that long. Now, we're going to talk again. We already had this slide yesterday about tail recursion and the stack frames. And we went through and drew this out yesterday with how this works on the stack. Is that one thing that's important to remember is that the recursive calls get made. Stack frames go on the call stack, and then as the recursive calls end, things come off of the call stack. Now, what we want to look at a little bit more in detail is what really goes on the call stack there. So when the function call is made, the currently running function has to save its local variables in a place called the stack. Now, why the local variables? Well, because of how computers work. The computer, to do anything, data has to be inside of the CPU. We can't say add this number that's out on the memory chip to this other number out on the memory chip. It's got to be inside the CPU. And they go into the CPU in a place called a register. And so there's a limited amount of those. The CPU we want it to be fast, so we want to make it as fast as possible. Means it's got to be as small as possible, so we don't have unlimited space inside of it. Obviously, we don't have infinite space, but there's a limited amount of space for these local variables. And because the function that we are calling is going to need local variables, also is going to need those registers, we save a copy of our registers onto the stack. Then we push anything that needs to be on there for the function we are calling. There's actually one hidden in here, is the return address. The return address, where should the code pick up when the called function ends? That goes on the stack. Then we put our program, our arguments, our function arguments, those get pushed onto the stack. Then we transfer control to that new function. When we transfer, yes, there is a little bit of repetitive from 370 in here. And this is stuff This is stuff that's not going to be on the exam, but we want to understand this stuff so we know why it happens, why tail recursion is better, other than just the fact that the stack space is limited. All this stuff takes time. So then when a function call is received, so once we transfer control to that function, all the program arguments have to be popped off of the stack, and those go into those registers, those things that we use as local variables. So then the function runs. When that function says, I want to return to where I started, well, at first it has to put the return value onto the stack. Then we have to get the address. We have to look on the stack to see where to return control to. When the return is received, we have to get the return value popped off the stack, the return address popped off the stack, the local variables that were saved on the stack, those have to get popped off and restored, and all of this stuff has to happen. So the more parameters a function has, the more work that gets done in 2A and 2A and 2B. So 2A and 2B, the more parameters we have, the more time steps 2A and 2B take. So the program stack supports these nested function calls. If we've got 6 nested calls, then there's 6 sets of local variables, 6 sets of parameters, and as each function returns, the return value goes on the stack. There's only one stack. Now, caveat, there's one stack per thread. In 281, we don't do multi-threaded programming, but if you want to learn more about multi-threaded programming, real huge inner working details, 482. And if you want to just do it, 494. The game design class does multi-threaded programming, I know. And also 4x there. I'm having trouble. New number. I think it's 440. 440. Nicole Hamilton's Build Your Own Search Engine class. There were groups in there that were running like hundreds of threads at a time, so they could index lots of web pages simultaneously. I think it's 440. I got to get more familiar with that number because we just made it a regular class. We just voted it in. So really, if you're doing multi-thread programming, there's one stack per thread, but we don't worry about that in 281. I just hate lying to you and oversimplifying things. The stack space is limited. Well, the computer memory is limited. The stack space is even more limited than that. The operating system decides when a program runs how much stack space it gets. And the nested function calls are limited by all of these things that we pushed on the stack take up space. So the more parameters we have, the more space each call takes, the more local variables, the more space each call takes, and the more space each call takes, the less calls that will fit on the stack. Now, I've never seen a function really with more than like 4 or 5 parameters doing recursion. Usually you've got like 1 or 2. And almost any environment I've seen, you can get 1,000, 2,000 levels deep, no problem. So if we have a program that, let's say it's recursive and we try to solve too big of a problem, or we messed up our base case and we don't hit it the base case and we just keep trying to go forever, the recursion won't really go forever. We'll run out of stack space, we get to what's called a stack overflow error, and the program ends. And in fact, there's a whole website built around that concept called Stack Overflow. So we've got the recursive and tail recursive, and we analyzed these last time. We talked about them and how the recursive and tail recursive versions of factorial, they both use O of n time, but the tail recursive one doesn't take O of n space. Now, I see a question from Joe about the tail recursive functions. They're not significantly faster because they still have to push all the parameters onto the stack. It's what they do is they actually replace they replace the previous calls parameters with the new calls parameters, but they still have to go into the stack so that they can be retrieved by the next call. So a little bit faster, but not significantly. Instead of like O of like 10n, it's O of 8n. So big O, no, it's not any faster. Real life, it might be a little bit faster. Okay, I didn't realize we had someone online answering questions. Thank you, probably Marcus. Maybe one of my staff also. Okay, so when we talk about recurrence relationships, we could have a recurrence relationship for the formula. We could do a recurrence relationship for the time, which we've done previously. We could also write a recurrence relationship for the memory. Usually, it's not necessary to write a recurrence relationship for the memory. It tends to be much easier to see. In actual code, we look at the data structures, we go, hey, there's a vector there of size n, that looks like O of n memory. So usually the memory is pretty easy to see from looking at the code and the data structures, looking at the recursive calls for extra space. If you pass structs by reference, basically it's a pointer, is the simplest way to think of it. It's almost right, and that'll get you through. Okay, so our power function, here's a new version of the power function, which if we really wanted to, we could use the default parameters again for a intermediate result. We could do the work to modify the result when we need to, and then when the recursive calls end, it's tail recursive. Now this one is not super critical to have a tail recursive version because like 2 to the 30th power will overflow the size of an, or actually more than 30th. If we go like 2 to the 33rd power, we'll overflow the size of an integer. If we do 2 to the 65th power, we'll overflow the size of a size t. So before we run out of stack space with the power function, we're going to overflow the numbers anyway. So this one's not critical to have a tail recursive version, but I wanted to show it to you just because we can use the default parameter again. So like we said, the stack space is limited. For even a linear function, we think of linear functions as really nice in terms of time, but it turns out the linear function could be completely unreasonable in terms of stack space if it's not tail recursive. So it doesn't mean we should always write tail recursive. Some things are not solvable in O of 1 space. If you think about in 280, let's do an example from 280. You talked about binary trees a bit, and you looked at a traversal of the tree, like an in-order traversal, where we call to the left subtree, then we do something like we print the current node, then we make a call to the right subtree. Because we've got these two recursive calls, one of them happens before we print and before another recursive call. This one cannot be tail recursive. This one can. But this function is not tail recursive because it's got a path that's not tail recursive. And so this one can't be written in O of 1 space. If we have a binary tree that's a big stick that goes left, 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 we could overflow the stack just trying to print out the contents of the tree. How do we overcome that? One way would be, instead of relying on the call stack, we could use a stack variable, kind of like we're doing in Project 1. We could use a stack variable, put the things on the stack that we still need to do, and then call them from the stack as we need them. If another way to do it would be to, later on in the semester, after the midterm, like in the week after the midterm, we're going to look at making a self-balancing binary tree, one that never gets too stick-like, And because it never gets too stick-like, the height never gets ridiculous. And so as long as the height is reasonable, like 2 to the, or if we've got n nodes, if the height of the tree is around log n, then we could have a billion nodes. 2 to the 30th power is a billion. We can have a billion nodes with a tree of only height 30. How do I get there so quickly? Got to learn some powers of 2. It'll save you time in the future. So 2 to the 10th is equal to 1024. Whoops, 1024. I started to make a power there. 1024, which is approximately equal to 1,000. So 2 to the 20th is approximately equal to 1,000,000. 2 to the 30th is approximately equal to 1,000,000,000. So if we had a balanced binary tree that isn't too stick-like, we could fit 1,000,000,000 nodes in height 30, and it wouldn't matter that we're doing recursive calls that aren't tail recursive, because we'll never go more than like 31 levels deep to get to a base case. Okay, so binary search, we wrote out a recurrence relationship for this last time. Let's make sure we believe this before we proceed. So if we do a binary search, we look at the middle. So we calculate where the middle is. We look at the middle location. And if that's the value we're looking for, then we can return and say, hey, I found it, or I found it at this index, or whatever we have to do. And if we don't find it at the middle, we look in the left half, or we look in the right half. Now, these halves may not be perfect. If I had like 8 items, I might say, ooh, well, here's the middle, and there are, let's see how it would work out. I might have like 4 elements on one side and 3 on the other, or I might have 3 elements on one side and 4 on the other. Because one of them is the middle element that I look at, the other 7 get divided up almost evenly. So almost evenly divided by 2 in integer world, sure, close enough. So I've got to do some constant amount of work, figure out where the middle is, look there for the value that I want to find, see if it's equal. If it's not equal, is it less than, is it greater than? And then either make a recursive call to the correct half, or just go back through a loop where I only look at the left half, or I only look at the right half. So the constant amount of work is the figuring out the middle and checking the middle, and proceeding to the next half. Doing that left half or right half is the T of n over 2. So now hopefully we can believe this really is the recurrence relationship for a binary search. And if it is the correct recurrence relationship, we've already solved this problem. We already solved that one, and we got big theta then log n. The question is, what if we changed it? What if I was doing something other than binary search, where I say split it into 3 pieces and I only had to look in one of them? Or what if I split them into 2 pieces, like in order traversal? What if I split it into 2 pieces, but I have to make recursive calls into both sides? What if I had the amount of work after the recursion or outside the recursion? What if that wasn't constant? What if that involved n somehow? Then we'd have to redo the recurrence relationship every time. We'd have to then solve it with the substitution method every time. And there's lots of recurrences that look like this, and many of them can be solved using the master theorem. Not all of them, but many of them. Now let's look at first a few general recurrence relationships that you're going to see. What is an example of an algorithm that exhibits that recurrence relationship? And then what's the solution? So we've already solved these ahead of time. So we've got the first one, T of n equals T of n over 2 plus C. And in here, to make it fit a little bit better, I didn't worry about the base cases. We can assume all of these have a base case. When n gets equal to 0 or n gets equal to 1, they've got a base case. So we're really interested in the complex part of the recurrence relationship. So this one we just had from the previous slide. Example is binary search, and we solve it, we get O of log n. If we look at linear search says look at index 0. If that's not what you're looking for, you still have to look at the other n minus 1 elements. Look at the, let's just say first, let's use a generic term. Let's look at the first remaining value. If that's not it, there's n minus 2. Let's look at the first one of those. So that's our recurrence relationship for linear search. We solved that one yesterday using the substitution method. We get O of n. Next one, tree traversal. So we are assuming here that we have split the tree into halves and it's not just a big stick. If we split it into halves, we still have to make a recursive call. That's the first two. We have to make 2 recursive calls, one into each half. So the divide by 2 means I cut it into 2 halves. The times 2 is I have to make 2 recursive calls. And if we solve that one, we get O of n. Now, for what we're doing, sanity check, I think that makes sense. If I want to print out every value in a binary tree, it should take O of n time because there's n things to print. If we look at a selection sort, bubble sort, what we call the elementary sorts, which we're going to do in a couple weeks, the elementary sorts tend to have a recurrence relationship like this, where we do something. Let's consider selection sort, which I believe you talked about in 280. Selection sort says, let's find the smallest value. So we've got to go through all n elements to find the smallest value. Then we swap that with index 0, and then we repeat that process for the other n minus 1 elements. So I find the next smallest element, I swap it with index 1, then I go to index 2 to the end. What's the smallest value from 2 to the end? Swap the smallest value with index 2. Let's try it again with it, starting at index 3. The slowness in recursion tends to be the fact that you've got all those things to push onto the stack. We can mitigate them, and we're going to talk about that a little bit later on, Bradley, how to mitigate that effects of recursion by reducing the number of parameters, how we'll do that, etc. But that is going to come up in the future. Okay, so if we've got our selection sort here, we know the elementary sorts, hopefully from 280, the elementary sorts tend to be O of n squared. And if we solve that one, we can do that. For the next one, some more advanced sorts, like merge sort and quick sort. There's the equation. If we solve that out, we get O of n log n for more advanced sorts. And so these are just some of the common recurrence relationships and examples of them you might see. So when we want to solve a recurrence relationship, we can write it out, we can substitute, we look for the pattern, we get the formula for the end. Another way is the master theorem, which we're going to talk about. The book CLRS talks about the recursion tree method. I find these tend to be, for me at least, easier than that. Selection sort is actually pretty simple in code, we'll see. Okay, so here's the introduction to the master theorem. It says, if we've got a monotonically increasing function, we'll come back to that one in a minute. So it's monotonically increasing if it satisfies this form. We've got some relationship, t of n equals a times t of n over b, and then we've got plus f of n. We have to have a base case, either t of 1 or t of 0. We've got to have some sort of base case. And we've got some relationships here. So it says a is greater than or equal to 1, b is greater than or equal to 2. Or really, let's change this right now, and I'm going to update the slides for this. B has to be greater than 1. It could be, in some weird world, it could be like some weird problem, I mean, could be like 1.5, and that would still be okay. So as long as b is greater than 1, and f of n is of a form, it says f of n is an element of the polynomials. So if it fits all of these criteria, then we've got a way to figure out what the big theta complexity is. Now, with the monotonically increasing, what that means is that as n becomes larger, the complexity goes up. It never ever goes down. If it goes down, then we can't use the master theorem. For real-world problems we're going to solve, the monotonically increasing isn't a problem. For the other ones, for a has to be greater than or equal to 1, b has to be greater than 1, f has to be of the form of a polynomial. Probably the most restrictive one is the f has to be a polynomial. The non-recursive work has to be in the form of a polynomial function. We're going to see an exception to that last one in a little bit, but in general, if we've got these three things, then what we do is we look at what is the relationship of a, how does it relate to b to the c power. So there's our a, our b, and our, our c comes from right here. Just a second, I need a drink of water. Okay, so we've got our a comes from what we multiply by, b is what we divide by, and c is the power of the polynomial. So if we figure out how a relates to b to the c power, it tells us which one of these three categories we're in and what the form of our final big theta takes. And in these equations, in the big theta equations, the a, b, and c there are the same a, b, and c that we got out of these formulas. So these are the same a, b, and c throughout. So let's look at an example here. So I've got a recurrence relationship that I wrote down. We've got 3t of n over 2 plus 3/4 n plus 1. So we got to figure out what are the parameters. A is equal to 3, that's the value out front. B is the divided by 2. And then c is equal to 1 because this portion is of the form, that's an element of big theta of n to the first power. That's it. The big O or big theta of that thing is a polynomial. Okay, so we've got our constants, 3, 2, and 1. We say, hey, how is A related to B to the C power? So 3 is greater than 2 to the first power. That tells us we're in case 1. We're in this first one. So if we're in this first one, then we can conclude that we've got the form big theta of n to the log base b of a, which is equal to big theta of n to the log base 2 of 3. Now, that is a little bit cryptic. N to the log base 2 of 3. I don't really have a feel for how complex that is. We're going to say this is approximately equal to. It is not exactly equal to, but it's approximately equal to big theta of n to the 1.58. So that's what the log base 2 of 3 is. I just wanted to get a feel for this. It's bigger than n to the first, but it's not quite as big as n squared. It gives me an idea. It's somewhere between linear and quadratic. Now, it is approximately equal to here. The log base 2 of 3 is exact. This approximation gives us a feel for it, but we would not want to say this is equal, because that 1.58 is just an approximation. So that gives us an example of using the master theorem. What I'm going to do here in the next slide is give people a minute or two and look at what is A and B and C for this problem. And you can think about it, write it down, you can type it into the chat when you find it, and then we'll proceed after. We'll write these down, and then we'll go through the rest of it together. Okay, so we got 2. All right, so A is equal to 2. Yep, that's out front. B is equal to 4. Yep, that's what we divided by. And C is equal to this portion. Well, this is the square root is n to the 1/2 power. All right, so that gives me my A, B, and C. So we want to know, how is A related to B to the C power? All right, so I've got 2. How is 2 related to 4 to the 1/2 power? Well, 2 is equal to 2. Okay, so that tells us we're here. So we're in this region. We've got big theta n to the cth power times log base 2 of n. Okay, so we've got big theta of n to the c power log base 2 of n. Well, n to the cth power is square root of n log n. Okay, and yep, I did it right. So we've got a hidden slide here just to double check, make sure I didn't make a mistake while I'm doing it. Okay, so we've got that big theta of square root of n log n. Seems like a strange sort of complexity. Square root does come up very, very rarely in complexity analysis, but it can happen. I've seen some odd things with really complex algorithms. I've seen a square root once. I've seen log of n a few times. Okay, here's another one. So what I want you to do with this one is step through the whole thing. Find A, B, and C, figure out which of the 3 cases it is, figure out the final form of the equation. If you're guessing that we've already done the first 2 and this is probably going to be the 3rd one, that would be a pretty good guess. So find the constants for these for A, B, and C, and find the final form of the complexity. Yes, you're going to be tested on the master theorem. No, I probably don't think it would be necessary for an interview. And when we do exams in 281, now, since you're going to be at home, we're going to let you use your slides, but still, I think it's a good idea. Even in the spring semester when we're doing an online exam, you should think about making a notes sheet. Make a cheat sheet with the things that you think are the most important that you're going to need when it comes to be exam time, that you want to be able to get to quickly. Like, hey, I don't want to have to go, ooh, I think that was lecture 5, slide 19. Or, no, I don't want to go through that. I want to have a cheat sheet ready with the master theorem on it so that when I'm looking at the exam and I need it, yep, I can pull it out there. Okay, so we're starting to get some answers here, and we had some talking while we're doing it. So, okay, so we've got A. Well, A is out front here. That's just 1 since there's nothing written there. We divided by 2, that's B. And we've got n squared plus n. Well, n squared plus n is an element of big theta of n squared. We take the highest order term, we eliminate the low order terms, we eliminate the constant on the highest order term, so C is equal to 2. Derivation of master theorem. Gosh, I have not looked at derivation of master theorem in a long time since I took if you take a grad level class, you'll do it. 477 might do it. 586 might do it. So here we've got ABC, so we've got our ABC. We say, how is A related to B to the C power? So we've got 1 is less than 2 squared. That means we've got to be in this case. And if we're in that case, it's just big theta of n to the C power, which C is 2. Big theta of n squared. So there we go. So we got that one right. Now, what I want to do is I want to go back through these. I want to go back through each of these examples and look at more than just using the master theorem to solve it, what does it mean when we are in this case, for example? So when we're in this case, we ended up with big theta of n squared. Well, big theta of n squared was the same as the non-recursive portion. So when we see that b to the cth power is greater than a, what that's telling us is the non-recursive portion is the bulk of the work. We started out with the non-recursive portion is n squared and our final complexity is n squared. That tells us that the non-recursive portion is the bulk of the work here. Kevin, I'll get to that question in just a minute. Let's go through these and I'll get back to that one. Okay, so in this one, when we've got the third case, the non-recursive portion is the most work. Let's go back to the first case that we looked at. In the first case that we looked at, we've got the recursion and we've got a log n there. Generally speaking, when we see this one, it's a little bit, sorry, I didn't go back far enough. Sorry, I want to go back to this one. So in this one, when a is greater than b to the c power, so when a is greater than b to the c power, we ended up with an n around 1.58. That's less than the polynomial portion. Or sorry, not less than, sorry. It's not less than the polynomial portion. I don't know what I'm thinking there. Generally what this means is that because it's greater than the polynomial portion, because a is greater than b to the c power, the recursion is the bulk of the work. Because the 1.58 is greater than the first power, the bulk of the work is in the recursion. Now when we go to this one, where a is equal to b to the c power, we end up seeing both of them in the recurrence relationship. The square root is in here, and the divide by 2 effectively. Notice we had 4 regions and we do half of them. Our divide by 2 is in there, our square root is in there. When a is equal to b to the c power, it tells us that both parts, the recursive part and the non-recursive part, are both contributing to the complexity. So when we've got the first case says the recursive is the most work, the last case is the recursive doesn't contribute much to the total work, and in the middle case, they're both contributing to the work. So Kevin, your question about the formulation in CLRS. This is a place where I think CLRS does you a disservice. The very first semester I taught 281 at U of M, I inherited slides from the previous professors, and they used the CLRS definition, and I glanced at it before the lecture, and I went, oh yeah, I remember that from when I took this class as a grad student, no problem. And I started teaching it, and I went through it, and people's faces were just blank. It was like fear and trepidation. And I went, oh my gosh, that was a terrible way to teach that. So I came back the next day with updated set of slides. I called it Master Theorem Revisited, and we went through this method. The two methods are equivalent in definition, they're equivalent in power. This one is way easier to apply. The one in CLRS is just as effective if you can see it. Okay, so when don't we use the master theorem? Okay, we can't use the master theorem if T of n is not monotonic. If the time function goes down at any point, such as a sine, we break the rule about monotonically increasing, we can't use the master theorem. If f of n is, say, exponential, doesn't fit a polynomial, we can't do it. If we can't express b as a constant, so if my what I'm dividing by can't be expressed as a constant, we can't use the master theorem. Now, like I said, there is a special fourth condition for some things that aren't polynomials. We'll get to that in just a few minutes. We also can't use the master theorem if it's a subtraction instead of a division. Master theorem is made for dividing by, it's not made for subtracting. So with anything that doesn't fit this, we've got to go back and use the substitution method or the recursion tree method. We've got to do it the hard way. But if it does fit this form of a times t of n divided by b, f of n is a polynomial, a is greater than or equal to 1, b is greater than 1, etc., we can use it. So now the fourth condition. The fourth condition is a little bit rare, but it does happen. So the fourth condition says if f of n is of the form big theta n to the log base b of a times log of k of n for some n. So this is a log power. This is like log of n, that value squared, log of n, that value cubed, etc. K doesn't matter here. What matters is this portion must fit the b and the a that we have from the original equation. So if it fits this form, then t of n is big theta of n to the log base b of a times log 1 larger log power, log k plus 1 power of n. And it's fairly limited. This is one, I would say this one's maybe fair game for a lab, not for the exam. So we might pull this one out on a lab. I won't promise we won't, but I will promise we won't pull it out on the exam. Now here's an example of using it, just so we can make it a little bit more concrete. So I've got this form, 2t of n over 2 plus n log n. N log n, now that's a fairly sort of common form. That's what it would take if we were doing like recursively doing a sort of a fast sorting algorithm there. So we've got from this, we've got a equals 2 and b equals 2, easy, multiply by 2, divide by 2, but f of n isn't a polynomial. However, it is in the form n to the log base b of a. Remember, it's got to be of the form n to the log base b of a times log of n to some power k. Well, this log base b of a, the n to the log base 2 of 2 is the same as n to the first. And that's what we've got here is n to the first. We happen to have in this case, since we don't have a power here, k must be equal to 1. So the form of this equation when solved is big theta of n log squared of n. Okay, now suppose you have a friend who maybe took 280 with you but isn't taking 281 this summer, and they say, hey, I've come up with a great idea. I've got a new way to find the maximum element in an unsorted array. I'm going to use the power of binary partitioning. I'm going to split it in half. And split it in half, I'm going to find the smallest value or largest value in better than O of n times. So what I'm going to do is I'm going to split the array into 2 halves. I'm going to recursively find the maximum of each half, and then I take the maximum of those 2. And you say, because I'm splitting it in halves, it's got to be better than linear time. And you say, no, I don't think so. So how could we give an intuitive argument? Intuitive meaning, how could I just describe this without proving it that we can't do this? What if I said, just a rhetorical question, how can you find the smallest element in the array if you don't look at all of them? To have a complexity better than O of n, you've got to not look at all of them. But if you don't look at all of them, how do you know you found the smallest one? So that's our intuitive argument. How do we do it with the master theorem? Well, we'd say I've got to write a recurrence relationship. Now, t of n is equal to, now let's write out the whole thing. We need a base case. Oh, it's basically a constant amount of work when n is less than or equal to 1. So if I get down to, and I divide my array into 2 halves, if I get a region that's size 1 or a region that's size 0, either one of those is a base case. Otherwise, I've got to look at the first half, I've got to look at the second half, and then I've got to do some constant amount of work to decide, oh, which one of those is the bigger value. And also I had to do some constant amount of work to figure out where the middle is. That's all in C1. Well, we can rewrite this as 2t of n over 2 plus C1. Aha, we can plug this into the master theorem. If we plug this into the master theorem, what do we got? We've got a is equal to 2, that's our value out front. B is equal to 2, that's what we divided by. C is equal to what here? Here's our polynomial portion. This is an element of, I'm running out of room, let's write it vertically. That's an element of big theta of n to the 0th power. Because it's just a constant, c is equal to 0. So we've got our a, we've got our b, we've got our c. We plug it back into the master theorem. We scroll back a couple slides, plug it in. We've got, let's find out which situation. How does a relate to b to the c power? Well, I've got, how does 2 related to 2 to the 0? Well, 2 is greater than 1. So if 2 is greater than 1, let's scroll back a bit to our master theorem definition. Okay, so there's our master theorem definition. Let's get rid of all those markings there. Okay, so we know we're in this case. We're in the n to the log base b of a case. So if we're in the big theta of n to the log base b of a, let's go back, I gotta find my slide. Okay, so we know we're of the form big theta of n to the log base b of a. Well, this is big theta of n to the log base 2 of 2, which is big theta of n. So, master theorem proves it. You've got to look at n elements to find the smallest one. All right, now what we're going to do in the last section of slides here is we're going to look at a bunch of ways to solve this problem. So, what we've got is we've got a matrix here, and it says n by m. When we say n by m, we mean this number of rows and this number of columns. Okay, so that's our number of rows and columns, and we tell you up front that it is sorted along the rows and columns. So the first definition says the value in table sub I sub j is less than or equal to anything to the right of it. The second rule says table sub I sub j is less than or equal to anything below it. So it's less than or equal to anything to the right of it, it's less than or equal to anything below it, and if we do that and we say, hey, find me a particular value. I want to find a particular value in here. Well, we could search every row and every column. That's O of n times m. That's too slow. We could, let's look at every row and let's do a binary search of each row. Or I could do m log n. I could look at every column and do a binary search of every column. That would work. These are actually still too slow. We want to do better than that. So let's look at how we can do that. And I'm sorry, I didn't realize that the 31 here, the page number is sort of bleeding through that. That's not meant to be a value there. Sorry about that. Okay, so let's look at our first idea. What I'm going to do is split it in half both horizontally and vertically. So I'm going to split it in half horizontally and vertically, and in this n, my definition of n is the size of one side. And to make things a little bit easier, what we're going to assume is that instead of n and m being different, we're going to assume it's n times n. Because we don't want to deal with right now two different variables in our complexity relationship, in this problem anyway. So we want to divide it in half along the size of one side, and then look at the recurrence relationship. So if I split it this way, what I'm going to do is I'm going to look at the middle element. From the middle element, I'm going to be able to eliminate one of these quadrants. For example, if I was searching for the value, let's say 11. I'm searching for 11. I look at the very middle value here and I say, okay, 9. Everything above 9 has to be smaller. Everything to the left of 9 has to be smaller. Everything in this region has to be smaller than 9. 11 can't be in there. 11 could be in here. It could be in there. It could be in there. I have eliminated one of the regions. I've got to recurse into the other 3. Alternately, if I checked for a different value, if I said, hey, I'm looking for, let's say, 8. Well, I know 8 cannot be in this region because everything, 8 is bigger than 9. Everything to the right of 9 is greater than or equal 9. Everything below 9 greater than or equal 9. It can't be there, but there could be. This value in the upper left of this region, that could have been a 9. There could have been a 9 there. There could have been an 8. I'm just looking for 8. There could be an 8 there. There could have been an 8 there. There isn't, but there could have been. So I could have eliminated one of these regions based on the middle. I could also get lucky. I could get lucky and say, hey, I found 9. That's right in the middle. I'm done. But if I don't find it right in the middle, I can do one of the other regions. So my recurrence relationship is T of n. Remember, n is the size of one side. 3t of n over 2 plus c. So there are 3 separate recursive calls I've got to make. I've got to make recursive calls to, say, this region, this one, and this one, because I eliminated that one. I'm searching for, say, an 8. I can eliminate 3 regions, or I can eliminate 1 region. I've got to make 3 recursive calls, and in each of them, n has dropped approximately by half. Now, it's not squares anymore, but it's close to a square, and we can solve the equation for this. In fact, we've already solved this one. Now, let's look at a different way to do it. Let's do a binary partitioning. And what I'm going to do is I'm going to figure out, I'm going to scan the middle column here. Alternately, I could use the middle row, but we've got it diagrammed out using the middle column. I'm going to scan down the middle column, and I want to find where the value should be if it was there. Now, of course, we could get lucky. I'm searching for, say, 14, and I find it, I'm done. But if I don't find the value I'm looking for, I want to know where it should be. So if I were to find out, let's say I'm searching for the value 11. I find out that 11 should be there. It should be between the 9 and the 14. Because it should be there, I look at what's right above and below where the 11 should be. The value right above me tells me it cannot be in the upper left, because that 9 above me tells it can't be in that region. The 14 below me tells me it can't be in this region. So I look at the value on either side of where the 11 should be, and that tells me which regions I can eliminate or not eliminate. And I'll always be able to eliminate 2 of them. Then we recursively process each of the other 2 regions. So, recurrence relationship for this. 2t of n over 2, I've got 2 regions, each of size approximately n over 2 is the size of a side. Cn, n here is my time to scan the middle column. Well, wait a minute, I could improve it by doing a binary search of the middle column. So I could do a linear search of the middle column, I could do a binary search of the middle column, and we're not going to solve all these equations yet. We're looking at different ways to do it. Okay, so we could use a binary search in the middle column, and then we get a different equation. Now, here's the different equations. We've got the first one we've already solved, binary partitioning. Master theorem can do it. The improved binary partitioning, that one is actually going to be a pain to solve. We had to do that one by hand. So here's the recurrence relationships for each of the, or sorry, the solution to each of those. The first one we already did. This is our approximately 1.58 power. The binary partitioning, we get, master theorem gives us big theta then log n. The improved meaning we did a binary search of the middle column. This gives us a big theta of n. So that's looking like the best possible. So this, basically the size of one side is about the amount of work we're going to have to do. So that one says, so far, this is our best solution. Now let's look at a different way to do it. And this one, we've got the code provided here. So this approach says, hey, let's start in a corner. Now let's look at how it works first before we look at the code. So let's say I'm looking for the value 13. I start in the upper right corner and I find a 15. Well, because it's 15, I know 13 cannot be below this because everything below it is bigger than that. Then when I go over, since I can't go down, I got to go left. So I go left one spot, I see an 11 there. Well, that's not 13. But 13 can't be to the left of it because everything to the left of it's smaller. It can't be there, so I've got to go down one. I go down one when I see a 12. That's not 13. It can't be to the left of there because everything to the left of 12 is smaller. It's got to be down. I go down to that 16. 16 is not 13, but I can eliminate all of those. I've got to go left. I go left. Everything to the left of 16 is smaller. I get to 9. 9 is not the 13 I'm looking for, but I can eliminate everything smaller than 9. I've got to go down. If things below 9 are bigger. So I go to 14. When I get to 14, that's not the 13 I'm looking for, but everything there is too big. I've got to go smaller. I got to go left. So I go left and I find the 13 I'm looking for. So let's look at the code here. The code says you give me a two-dimensional matrix of integers, and this thing has to be a constant. Got to be a constant for us to pass a 2D array to a function. And I give you n. I tell you what n is because we're going to need it for the looping conditions. I've got to know the target value I'm searching for, and because I've got to tell you what row and column is it in. Because I've got to tell you what row and column it's in, I've got to effectively return two values. Now I could return a pair, but I hate using pairs. So what I'm going to do is I'm going to return a Boolean to say, did I find it or not? And I'm going to have you give me two row and column variables that I can receive by reference and I can modify them. When I'm done, if the Boolean is false, you're not allowed to look at the row and column because I gave up. I modified row and column all the way through, but if I return false, you're not allowed to look at those values. They don't make any sense. But if I return true, then the row and column variables that I've been modifying are the actual row and column of the value we're searching for. So what about that line 3? So that line 3 says if the target's less than, I'm going to get rid of some markings here on top of this graph so we can see that table there. Okay. So the first line here, line 3, says, is the target less than the upper left? Oh, that's the smallest value. Is it smaller than the smallest, or is it bigger than the biggest? If that's true, it's just not in there. We're not going to do any searching. So we don't want to search if it isn't in there at all. Then we assume, this line 5 assumes it's in the upper right corner. The rest of the code does what we checked. We go through, if it's too small, we change the row. If it's too big, we change the column. Otherwise, we've found it. Now, before we get to the complexity of this, let's modify. Could we modify this? If we modified the code, like at line 5, could I start down here? Could I start with that value and I say, hey, I'm searching for 13. Well, that's not 13, but if 13's in here, it can't be to the right of that. Everything to the right of 18 is bigger than 18. I've got to go up. I find a 10. Well, that's not the 13 I'm looking for, but everything above that 10 is too small. We can eliminate that column. I've got to go right. Hey, look at that. I found the 13 I'm looking for. So that works. I could start, the code starts in the upper right. I can modify the code, line 5, to start in the lower left, and I would have to modify the ifs at lines 7 and 9 and what I modify at lines 8 and 10 to change the row and the column differently. So if I modify basically line 5 and 7 through 10, I can make this work from the lower left corner. How about if we start in, I'm going to erase everything here. What if I say, hey, let's start in the upper left. I'm searching for 13. It's not here, it's somewhere in the rest of the grid. That didn't help because everything's bigger than 1. And if I start down here in the lower right at the biggest value, I get no information from looking at it. I don't know whether I should look left or up. I have to do both, so it doesn't get any better. So I could, okay, so what if the 10 was 16? If the 10 was 16, then this would break the rules because it's not increasing, it's not non-decreasing from left to right. So there couldn't be a 16 there. Can't put a 16 there. The biggest value I could put here would be 13, and then I would find it. I would find a different 13 from this corner and this corner. Would find, one of them would find this 13 and the other would find that 13, but I would still tell you, hey, there's a 13 in there. I found it. So with that improved binary partitioning, the fourth condition I think doesn't fit actually. I think it goes beyond that. I think the big theta of n to the log base b of a times log n to the kth power. I think the log base b of a doesn't come out to be the right form. So I actually had to do that one with substitution and solve it. Painful, ugly. Okay, so now we know we can't start in the smallest value or the biggest value. We can start in the upper right, we can start in the lower left. What's the complexity of this one? Well, in this one, let's look at the worst case complexity. Let's look at the worst case complexity of this. Every time I look at a value, I either move left or I move down. The furthest I could go before finding out that it's not in there would be all the way over to here. Like if I was searching for the value 18, I would have to keep going. I would go, if I was searching for 18, whoops, I don't want a keyboard. If I was searching for the value 18, for instance, I would go down, then left, then down, 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 left, 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 left. And I would have to do that approximately 2n times. So this one is a low event at worst. We could always get lucky and say, hey, find me 15. There it is in the upper right. I'm done. I could always get lucky and find in the first location. But the worst it could possibly be is about 2n. I either move left or I move down, and eventually I get to the point where this while condition fails. I've run out of places to look. And if that while condition fails, I get to line 14 and I return false. So the most I can possibly do is go like left, down, left, down, left, down, or left, 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 down, down, down. But the furthest I can go is to reach the opposite corner, and that's going to be about 2n steps, which is O of n. Now, there's a website here where he's got a bunch of the data of doing this. He's got all the source code available, and the table here of running it. So he's got the algorithm and the runtime. of running it a million times with like different random arrays and random values to search for. So binary searching. So this is, he didn't even do the let's linear search every row. So that one was just off the table. So looked at binary searching every row or binary searching every column. Binary searching every row, pretty okay. Diagonal. Diagonal binary search is basically saying, let's, instead of searching the middle row or middle column, let's search the middle diagonal, like from upper right to lower left, I think it goes. And that one is even worse than binary searching the middle row or middle column. Stepwise linear, which is the one we just did, stepwise linear comes out to be second best. Pretty good. The quad partitioning, where we had that was the big theta of n to the log base 2 of 3. That one, okay, about 17 seconds. Oh wait, not second best, it's oh yeah, second best, very good. Okay, so then the binary partitioning, where we linear search the middle row or middle column, does almost as good as the stepwise linear. And the improved binary partitioning, where we binary search the middle row or binary search the middle column, comes out to be the best. Yet you're true, that is Manhattan distance. So it turns out that although both of these are big theta of n, at their worst case, they are O of n. They are O of n. They can't be worse than n. They are big theta of n in the worst case. So those are both O of n, but the improved binary partitioning does really a significant amount better. Why? This is a good question to talk about why. And Professor Darden might have done this. I didn't watch all of his lecture. Why? When we ask you why in computer science, a good starting point is efficiency. Why would someone do it this way instead of that way? Why is this inexplainable thing better? Well, when we ask you why, efficiency is a good place to start looking. It is not a sufficient answer to say, why did we do X instead of Y? And you say efficiency. There, I got all the points. No, it's a good place to start looking. So we already know this one is more efficient. Why is it more efficient? And the answer is the cache. And when we talk about the cache, we're talking about how computers work. And we're going to come back to this idea of the cache in another few lectures. Let me take a look here. When we do the STL, another 2 lectures. So that will be Professor Darden on Thursday. We'll be talking about the STL. So I'm going to talk about the cache a little bit here because we've got a little bit of time here. We're done a little bit early. I want to talk about what the cache means. So when we run a program, remember we said to do anything with data, it's got to be inside the CPU. We got to get it out of the memory chip and into the CPU. The CPU size is really, really limited on how many things we can keep in it. Like the biggest I've seen is like 32 registers. So we could keep 32 values inside the CPU. Well, what the computer architecture does is, and I'm going to discard, I'm going to add a new blank slide in here. Oops, not the layout. I want a new slide. Wrong button. Okay, I want a new slide. And then, oh gosh, now you get my weird view. Okay, hold on. I got to flip this. This is going to be annoying. PowerPoint has a weird bug in it where if I exit and come back in, it looks weird. Okay. All right, so we've got our CPU, which is fast. And we've got our memory, which is our, if you've ever looked at a computer, this is called DRAM. This is like, hey, I've got 32 gigabytes of DRAM. This stuff is slow. Compared to the CPU, it's slow. Even if you paid extra money to get overclocked memory chips, it's still slow compared to the CPU. In between, what the computer architecture people did is they said, hey, let's put an area of memory in here. We're going to call it the cache. And the cache is going to be pretty fast. fast like either just as fast as the CPU or maybe a little bit slower. When I say main memory is slow, I'm talking like 100 times slower than the CPU. The cache, when I say it's fast, we're talking the same speed or maybe 2 times longer to get to something in the cache. And really, it's more complicated than this because the cache might have 2 or 3 levels, but don't worry about that. The idea of the cache is that we want it to store the most recently used stuff. So, things that are in memory, like, hey, my whole vector, my big vector is out in main memory, but when I want to work on it, I need to get it into the CPU. So, it turns out also how the cache works is when I say, go get me something from memory, like I said, it might take 100 cycles to go get one value from memory. But if I get a block of consecutive memory out of the DRAM, I can get, so if I get one location, the cost is, let's say, 100. If I get 8 locations, the cost is like 107. So when the CPU says, hey, I need this value, that request goes to the cache. The cache says, hey, I don't have that value. I'm going to go out to the memory and tell the memory, go get me that value that I want and the 7 things that follow it and put a copy of them in the cache. And now I can hand them to the CPU really quickly. This right here is called a miss. It's not in the cache. I missed seeing it in the cache. I had to go out to memory and get it. So we go retrieve it from main memory and the 7 values nearby. So then this one was a miss. It had to be loaded from main memory. But then, because of how programs tend to work, programs tend to exhibit what's called locality of reference. What this means is that if I say, hey, look up vector sub I, what's probably going to happen right after this? I'm going to increment I, and I'm going to look up v sub I again. I'm going to look up the next thing. They are going to be fairly local. Subsequent references to memory tend to be close together. So I'm going to look at v sub, say I'm going to look at v sub 0, then I'm going to look at v sub 1, then I'm going to look at v sub 2. So because the cache grabbed 8 consecutive locations at once, I got a miss for the first one, then I get 7 hits in a row, all fast, 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 fast. Then when I go to, say, index 8, it's not in there. I got to go out to main memory, I get a miss, I load a new block into the cache, and then I get 7 hits all in a row. So this is exactly right, Kevin. That is why linked lists are so ineffective, is because they aren't laid out consecutively in memory. Because they aren't contiguous, you can cache the memory, but the prediction that says the next thing you look at is going to be nearby fails with a linked list. So that's what's happening here when we see these 2 different ones where this is O of n, this one is O of n, but this one is significantly faster. This one makes a better use of the cache than that one does, a little bit better. It tends to retrieve addresses. It tends to retrieve addresses above, but it might go below also. Here's the fun thing, Joe. Unless you're a CPU cache designer for Intel or AMD, you don't tell normal people like a professor at U of M how your cache works. So the people who really know how the cache works in the chip, they work for Intel, they work for AMD, they've signed confidentiality agreements, They cannot tell us how it really works. But we've got a pretty good idea how it works. And I'm not up on the latest what's the best guess we have about how they really work, not my area of research. But so plus I is a bit better than minus minus. Tends to be. Although minus minus will catch up eventually because it'll load them in blocks. It'll notice that, I think the cache should notice that the block is going down, and then because of that it should grab things. It should grab from end of chunk to beginning rather than beginning to end of chunk. But it is, yes, it's a secret recipe. So if you want to really, really know how crazy this stuff is, take EECS 470. Yeah, I will warn you, EECS 470, extremely heavy load. You've got to take EECS 270 first. We have master students who come to U of M in architecture with a degree from some other university. They've already got an undergrad degree in computer architecture, and they take our 470, and some of them drop it because they can't handle it, because 470 is such a workload and such detailed work to design your own CPU and get it all working. One of my former IAs for 281, he left me. He took a job with 470, but I'm happy to see, I knew how smart he was when I hired him, and I'm happy to see 470 get a really good person like him working on their staff. So that's the explanation of why cache. Now, is cache going to be on the exam? No. But we need to know it to understand why sometimes when we see this thing is slower than that thing, why is it slower when theoretically they're the same? Sometimes the answer is the cache, and it's good to understand how it works so that we can see those and understand why some things work better than others, but how the cache works is not going to be on the exam. So last slide here, a couple of things. Actually, don't do that. Let's cross that one out. Don't do that. The master theorem in the CLRS textbook is ugly. The method we gave you is much easier to apply in practice. In theory, they are the same. In practice, the one we gave you is a lot easier. Okay, so that's it for today. We're done just a few minutes early, and I'm going to get some lunch, and I'll see you in office hours in about an hour. I'll stick around here for a few minutes in case there's any last minute questions, though. Okay, classes, no. Cache is not the reason that we use classes. One thing is slightly related to that. Like if I have a vector of, say, a struct or a class containing 3 things, that's better than 3 separate vectors because I'll get better cache usage of a vector of classes or a vector of structs than I will with 3 separate vectors. And also, really, its big thing, though, is an organizational issue. So a vector of structs is slightly faster than 3 vectors of single things, but it's really organizational and code readability, etc. It will make the code a little bit faster, but not like orders of magnitude faster. But it makes it much easier to read if it's well organized. But as someone pointed out earlier, cache is a reason why linked lists seems great on paper, but it's not always great in practice. And like I said, 2 lectures from now when we do the STL, we've got a set of slides at the end that go through different STL data structures and how well they compare with different operations, like if I insert here or if I insert there, etc. Well, like I said, we've got a textbook. We chose the best textbook for algorithms. We chose the best textbook for algorithms is CLRS hands down, but it doesn't make everything as clear as it could be. No, Bradley, it's not quite that one also. So, although indirectly it is, Bradley. So the reason we put big ones before smaller ones is that everything in memory must reside at an address that is a multiple of its size. So let's answer that question with a diagram here. So if I've got a struct, I've got struct A, and in here I've got like an int A, bool B, int C, bool D, int E, and bool F. Okay, what happens is every integer must start at a memory address which is a multiple of 4. So for this one to start at an address, so let's just say this starts at address 0. Then this one goes at, it takes 4 bytes. This one goes at address 4. This one must go at address 8, which means there's 3 bytes in here wasted. And then I've got an integer, I've got a Boolean, I've got another 3 bytes wasted. Then I've got an integer, I've got a Boolean, I've got another 3 bytes wasted. If instead, so this structure takes up basically 1, 2, 3, 4, 5, 6. 6 times 4 is 24. Now I'm going to erase part of this, and then I'll get questions are flying by. We'll get back to those in a second. Let's say we redo this in a different color. Let's say I say int A, C, E, bool B, D, and F. Oops, semicolon. So now this takes 12 bytes. This takes 3 bytes plus a gap of 1 for the next one. This is 16 bytes as opposed to 24. We saved a lot of memory. So this is a memory use issue. Now indirectly it will affect our speed a little bit because I wasted time loading 24 bytes when I could have loaded 16. So it's majorly space, decent effect on speed also. Let's see. Okay, cool. Yeah, the CLRS is a great reference. It's a great reference. Like I said, I kept mine from the time I took a class that used it until I came to U of M and got a new edition. And now I have the new edition, and I'll keep that one until maybe I get a new edition. But as a professional computer scientist, CLRS is a great reference, a great resource to have on hand when you need it. Okay, looks like I've taken care of all the questions there. So I'll see people in office hours.